look at this, and if it starts looking blurry, you have to say stop, okay? Oh, hold on, are we going? Nobody said anything.
Yes, we're recording.
I was going to have some dramatic intro. Okay, sorry guys. Okay, so today we're going to try something different, I think, just for fun. We're going to try using the blackboard. So we're going where no person has gone before. If it doesn't work out so well, if it's looking like it's not clear, because over here we can see the video. You can't see it because I would have to pan over, but over here the students in the classroom can see the video, so they're going to let me know if it's not clear, okay? And then I'll switch back to the document camera. But for now, I think maybe we'll try the video. Well, we'll try the video and the blackboard, because I like blackboard. I'm just curious. I'm going to take a very scientific study, especially it's going to be really unbiased after I already disclosed my preference. Tell me not to. Like in terms of teaching modalities and medias, okay? How many people? And you can put your hand up for more than one, I guess, okay, if you want. Like, how many people prefer Blackboard in lectures? Okay. How many people prefer PowerPoint slide kinds of things in lectures? Wow. How many people prefer document cameras in lectures? Okay. So, okay. Wow. That was quite overwhelming. For the people out in TV land, we had like 4 people put up their hands for document cameras. Nobody put up their hands for PowerPoint slides. And it was virtually unanimous because there were a couple people who voted twice. It was almost unanimous that almost everybody put up their hands for Blackboard. So that was quite dramatic, actually. That, more so than I would have expected. Okay. Also, I think we can put on the light onto the board. Where is the control for the light on the board? The light on the board. The light. Does anybody know how to control the light on the board? I'll worry about it later. Okay. Maybe could you figure that out for me, so I don't waste lecture time? Okay. So today, what we're going to do. Okay. So for the first week or two, I hope you don't mind, I have a standard formula, which is I keep reminding you. You have to read. What is it called? The notes, the book, whatever you want to call this thing. You're going to read it, right? How many people read it for this section that we're doing today? Be honest, okay? Oh, not everybody put up their hand. But it's actually good because it shows that the people in the room are actually honest souls, okay? But you really do need to do that because otherwise what ends up happening is that it's really hard the way I'm going to structure this is I'm just going to overview it. I'm expecting you to know it first. Okay? So everybody repeat after me one more time, okay? I promise to read the notes before I get to class. Thank you. You're very loyal students. Thank you. Okay. Now, so today we're going to talk about something which is pretty central to this class, okay? Which is 2 kinds of methodology. So one thing that's really fundamental in this class is that we talk about estimation, okay? So estimation is kind of a little bit of a boring word, but it's a very important concept, okay? So what happens in probability, you have this idea of estimation. So actually in 600, if you take 600, which is our introductory graduate level probability course, and there's some equivalent course in stat, whose number I forget. And most universities have a class like this, okay? That you learn about the structure of probability, okay? And that's fine, okay? But it's like learning about models. So it's like you have like learning about a wrench, okay? A tool. But it doesn't tell you what to do with it, okay? Probability by itself, some might argue, by itself is not terribly useful. It's kind of interesting, but not terribly useful. Where it really becomes useful is when you have estimation. Because probability says, okay, estimation tells you how to answer a question. So the question becomes, what's the value of some unknown? And then estimation is a way of using probability to try to determine the value on some unknown quantities, okay? Now, there's actually, and of course everything I'm going to say here is like oversimplified, but there's two sort of extremes, like in the world, 2 is the smallest number larger than 1 that's integer value, okay? I didn't know if you knew that. So it turns out that 2 is kind of a useful number, right? Like binary trees are, if every node only has 1 branch, it's not a tree, it's just a line, okay? So 2 is sort of the smallest number that's interesting, okay? So, it's often interesting in the world to say, okay, you have 2 poles, okay, and you vary between the 2 poles. So a wild oversimplification of the world is to say, okay, well there are 2 extremes and you kind of move between them, okay? We talk about this a lot in life, okay? Sometimes it's actually a excessive oversimplification, but it's useful. So in probability and estimation, there's 2 extreme views that are popular, okay? One is the Frequentist view, okay, which holds that the things that you're estimating are just unknown numbers, okay? And the other view is the Bayesian view, which holds that the things you're estimating are random variables, okay? So these 2 viewpoints lead to very different philosophies, okay? And as an engineer, I'm kind of agnostic. I'm happy to use whichever method works, okay? And I mix and match these techniques, which is really going to get you in trouble because, then everybody dislikes you, okay? But the thing is that, but they're what it really comes down to is that the Frequentist view tends to be useful when the number of observations, and the observations are inevitably random variables, when the number of observations is large compared to the number of unknowns. So if you're trying to estimate the mean and variance from a population of individuals, the Frequentist viewpoint is a good one because you only have 2 unknowns, the mean and the variance, but you have lots of data. You have, you could collect the height of a lot of people, okay? So you might have thousands of measurements, but you only have 2 unknowns, okay? The problem with the Frequentist viewpoint is it's pure. Oh, by the way, there's another thing I like to talk about, which is the, oh gosh, I'm really going to get myself in trouble here, but I can't help myself, okay? So on this spectrum, on one hand you have the pure viewpoint, and then I call the realm of the unholy, okay? It's when you actually do the stuff you need to, the gruesome, ugly, ad hoc stuff that gets the job done sometimes, okay? You kind of close your eyes a little bit. As an engineer, sometimes we have to make nasty approximations and really do stuff that's just not very pure, okay? But we're getting the job, okay? So we have to be pragmatic. So we have that, and the Frequentist viewpoint, in my view, is very pure. It's not trying to make any approximations or assumptions about the world which could possibly be invalid. But the price you pay for that is that sometimes can't get the job done, okay? So now the problem is this: if you have more unknowns than knowns, okay? So then you've got a problem. It's like you have a set of equations. If you have 5 equations, each of which have 10 unknowns in them. How do you solve that? So one option is to just say, well, this is impossible. I learned the theory, and the theory says this can't be done, so we're all going to give up and go home, okay? But the problem with that is that then your employer might say, you're fired, okay? So, sometimes you have no option. You have to get the solution. You're like, the asteroid is heading for the surface of the Earth. Tell me what to do, okay? And saying that you can't do anything is not a useful option. It's like in the Apollo 13 movie. How many people saw the Apollo 13 movie, where they say, failure is not an option. Do something, okay? Okay. So that kind of brings us to the Bayesian approach. And the Bayesian approach gives us sort of a framework that's a formal framework for handling problems that otherwise you just really can't solve very effectively because you have more unknowns than knowns, okay? So if the number of unknowns is large compared to the number of knowns, then typically you're going to try to use the Bayesian framework, or sometimes, and in the other case, you try, if the number of knowns is much larger than the number of unknowns, then you tend to use the frequentist. Now, that said, people who are diehard believers in the different viewpoints would very be very unhappy with what I just said. They would say, if they were frequentists, they would say, oh, well, that's completely untrue, because in fact, the frequentist framework can solve all these problems, okay? And the way they do it is by adopting a regularized or a penalized maximum likelihood estimation framework, which looks surprisingly like a Bayesian approach. Okay? Okay? And the way in the Bayesian would say, that's not true, we can solve any of these problems, okay? And the way they would do it was by adopting a framework which looks surprisingly like a frequentist approach, okay? So you can split hairs about this, but basically, what it comes down to is, what I think, I stand by what, get mad at me if you want, but I stand by what I say, which is that it's best, the frequentist approach is best when you have a small number of unknowns. The Bayesian approach is when you have a large, and guess what? Sometimes you have a mixture of both. You have a few unknowns, okay, and then you have a lot of unknowns. You go, well, that doesn't make any sense. Oh, well, let's say this. You're trying to, say, form an image, okay, from a microscope. And the microscope, the image will have billions of pixels, okay? But maybe you only made millions of measurements. But in addition, maybe there's like 3 or 4 parameters that you don't know about the microscope. Like there's some kind of voltage offset and some things like that that are hard to measure and need to be calibrated, okay? So what you really have is you have a problem where you have a few unknowns, okay, and billions of unknowns. But these are so you can use, this is really unholy, and you'll get yourself into lots of trouble with both groups because they'll both be unhappy with you, that you can use the frequentist approach for the small number of variables, and you can use the Bayesian approach for the large number of variables, and then everyone will dislike what you did, okay? But it's effective, okay? So that's the idea. So this is how it's going to work. So let's start off with the frequentist approach. So with the frequentist approach, first of all, what happens is you have y. Y is a random variable. Can you read that? Oh, yes. I just have to move over a little bit. Actually, let me do this. Okay, that's the one side of the board. And this is the other side of the board. No. So random variable, I'll abbreviate as RV, not to be confused with recreational vehicles. Okay. Now, what happens is that if I have something like, I'm going to make sure my notation is correct. So I have some function t of y. Okay. So t of y is what is called. This is a statistic. Okay? Any function of a random variable is called a statistic. Okay? Now, last time I told you also that in some cases a statistic is what's called a sufficient statistic if it has certain properties. Okay? And you can go look at those properties. But basically what the properties mean is it's a sufficient statistic if it contains all useful information from the random variables necessary to estimate the parameter. Okay? Now, the definition of a sufficient statistic depends on the concept of a parameter. Now, what will happen is that, let's say y is a random variable and it's distributed as p sub theta of little y. So that thing is not a random variable, that is a number, okay? And this is a parameter. And what happens then is, if you consider p sub theta, these are a set of functions, parameterized by theta, a member of omega, right? Some set. And this thing here is that in focus? Does that look okay to you? Can you read it? Yeah, I think it's probably good enough. It's not perfect, right? But tell me if it gets too blurry. So this is what's called a family of distributions, okay? Okay. So in a frequentist world, this parameter theta is not a random variable. It's just an unknown, okay? And we need to select the value of the parameter that corresponds to the observations we actually had, okay? So we say that a parameter is a sufficient statistic if it has to, if you look in the definition, it turns out if the structure of this, essentially what it comes down to is that this probability density function can be written as a function of the sufficient statistic, okay? That's a loose statement. Look at the formal definition, okay? And if that's the case, then the sufficient statistic contains all the information we really need in order to estimate the parameter, okay? Now what will happen is this. Now what can happen is this. We'll take, we'll form then an estimate of the parameter theta hat. This thing is a random variable. So here we have t sub theta of little y. That thing is a number. That's a parameter. That's a number. So I'll put here, I'll keep a taxonomy of all the things we have. Y is a random variable. Theta is a number. That's not a random variable. But theta hat, which is going to be equal to some function of y, any function of y is a random variable. So this thing is going to be a random variable. So theta and theta hat come from two different categories of things. Yep?
What's the little y in your taxonomy?
Oh, the little y is just, it's a variable, a conventional variable, so it's a number. But really, this is an artifact of the bad notation we use in engineering for probability, okay? Because, see, the problem is this, and let me just make a quick aside, that we have a bad habit. So in math, they typically will say, f is a function, okay? But in engineering, we have this bad habit, which I'm not going to attempt to break because it would confuse everybody, that they write f of t is a function, okay? Okay? So, we've got to put something in here. This is just an independent variable, okay? So it's just the argument of the function. So I can put anything, and often that's where I like to put happy faces, okay? Or sometimes you can do this. You can draw a little house, okay, if that makes you happy. You have a little door there, okay? So your variable can be anything, okay? It could be a little splotch of ink, okay? So this is nothing, sort of, okay? It's just our bad notation. It's the input to the function. So but people tend to confuse this with the random variable, okay? Now, what's really going to get nasty very soon, okay? And when I say very soon, I mean like in the next few minutes, okay? Is that it's very important you keep track of the fact that this is not a random variable, okay? And the reason is, in just a minute, I'm going to actually take that probability density and I'm going to actually plug y into it. Which, if you weren't confused before, you'll be confused then, okay? Because I'm going to actually take this function and put the random variable in it. Okay? And you say, why would you want to do such a horribly confusing thing? Because it's useful, okay? Now, when I do that, this thing here, and by the way, I'm going to also take the log of it. So I may as well just do that now, right? This thing here is now a function of y, right? Okay? Actually, it's called the log likelihood, okay? So this thing is this thing a number or a random variable? This is a random variable. Because it's a function of a random variable. Okay? So I'll put here I'll put here L of theta. That's going to be a random variable. Okay? So one of the most important things, I think, to learn this material is to keep track of what type of thing everything is. Okay? Okay. Now, So now, what's going to happen is that, so now theta is going to be a random variable. Theta is going to be a random variable. It's going to be c of y, okay, some function of y, okay? And, okay, now we'll say, I'm going to erase this thing, okay? Just a minute, I went off track for just a moment to get this idea across. So what's going to happen is this. We'll say, so the concept here is that theta is a random variable that somehow approximates the true value of theta, okay? So theta hat approximates theta. That's a problem because one's a random variable and the other is a number, so we have to decide what it means to approximate it, right? But we'll say that, theta is unbiased if the conditional expectation of theta hat, right, given y, assuming that theta is the true value, is actually equal to theta. So so let's say, there's a lot of thetas playing around here, okay? But let's say that theta is the true value of the parameter. And then we'll say, okay, now theta is the true value, we'll look at the conditional expectation of t of y, this function, which we call theta hat, condition on the value of y, right? And, oh, no, I got this all mixed up. So the conditional, I don't even need that, okay? It's this. All right, yeah. So, okay, if this is true, so it seems pretty reasonable that if theta is the correct value, that the conditional expectation of, that the expectation of theta should, theta hat would hopefully be theta. And this would be unbiased. Oh, I should write this. Unbiased. The one problem with doing this stuff here is that any errors you make are like there for historical inspection, and I make lots of errors, which is why I have the notes, because I try to be careful that that's the correct error. Okay, so this is unbiased. Now you would say, oh, well, any reasonable estimator should be unbiased. Not necessarily. Okay, in fact, this entire class is mostly all going to be focused on biased estimators, okay? So, okay, because it's going to turn out sometimes actually having bias can be useful, okay? Okay, now, then also we can compute the variance, so we can have the variance I'll just write it like this. The variance is the expected value under theta of theta hat minus theta bar of squares. Okay, that's the variance. And theta bar here is, we probably can't read that all. I'm running out of space. Theta bar is equal to the conditional expectation, is equal to the expectation of theta hat, right?
Let me just make sure I wrote that correctly.
Yes. So this is the mean of the variance. This is the mean of the parameter under theta. So theta bar is going to be a function of theta. I know this is confusing. You're going to have to read this carefully, and even then it's going to take you time to get your head around it, okay? Yeah?
So, do we use unbiased estimate because we can find unbiased, or is there any other way?
No. Okay. So the problem with unbiased estimators is that we're going to see in practice there's a trade-off between bias and variance. So you can have the purity of an unbiased estimator, but the price you pay for that in many situations is that the variance can get large, where large could be infinite. So if you have like more unknowns than you have knowns, then, well, basically what's going to happen is any unbiased estimator is going to have infinite variance, okay? So what we do is we pay the price of making some assumptions about things, and the price of making the assumptions is that the bias will be non-zero. Okay. So you know, just to give a quick intuition, one thing to keep in mind is that an estimator is unbiased if this relationship holds for all values of theta. So this has to be true for all theta, okay? So a way of explaining that is this. I wish we could do, you know what I needed to do? I needed to do something where I pan the camera so I can get a little piece of new blackboard to work so I don't have to erase things. Okay, so here's an example. Okay, so let's say you have a clock, okay, and with just one hand on it, so it's easier. It's a one-handed clock, okay? Now, what happens, you want to estimate what the position of the clock hand is, okay? So I can say, oh, well, the position of the clock hand is theta hat is equal to 1, okay? Well, the variance of that estimator is 0 once an hour, okay? So, the problem with this example is it shows that if you try to design an estimator, so this estimator you say was absolutely a horrible estimator, okay? But it's not a horrible estimator when it's actually 1 o'clock. It's a stupid guess, but it's correct once an hour, okay? So, the point is this. You have to not just be right sometimes, you have to be, this estimator is better than any other estimator at 1 o'clock, okay? But the idea in an estimator is not just to be best sometimes, it's to be uniformly good, okay? So the problem is, how do you formulate that? You need to put some constraints on the problem, and unbiasedness is a good place to start, but it has problems, okay? Now, okay, I think I'm going to erase this at this point and start, so the mean square error so the mean square error with an estimator is going to be the variance plus the bias square. So the total square error is the sum of the square of the variance, or the sum of the variance and the bias squared. You can prove that. Okay. So what's going to turn out is that in some cases making the bias 0 you can do, but it tends to make the variance very large. Okay. There tends to be a natural trade-off between these. Okay. Now, the Frequentist. Okay. So now in the Frequentist framework, theta is a number. The most common, perhaps the most commonly used Frequentist estimator is what's called the maximum likelihood, or I'll just write ML estimator, okay, or MLE, okay? The ML estimator is this. It's the value of theta, which is the arg max over theta, over the valid values of theta, of P of theta, and we actually plug the random variable y into the density. So this is where the confusion comes in that I described, okay? Seems like a reasonable thing to do. You took the density function and you only found the parameter which makes the probability of that specific observation the greatest, okay? Now, that's equivalent to taking the arg min over theta of, I'll let you figure this out, a log of minus the log of P of y. It's the min because I took the negative, and I can take the log because the log is a monotone increasing function. So maximizing the log is the same thing as maximizing the function. Now, I didn't describe that arg. Arg means that this function doesn't return the value of the function at its maximum or minimum. It returns the value of the argument that achieves the minimum. Now, there's some issues here because the minimum, there may not be a value of the solution may not exist or it may not be unique. There can be all kinds of things that go wrong, but let's not worry about that. Let's just assume that it works. And then, in general, if the thing's differentiable, a necessary but not sufficient condition for this maximum likelihood estimate. Oh, by the way, this thing is a random variable, right? Because it's a function of a random variable. Why is a random variable? And I minimize this so that this whole thing is a function of a random variable, so that has to be a random variable. And one way I can write it is I can say a necessary condition is that the derivative of the log of p sub theta of y d theta equals 0. That's often how you go about finding the maximum likelihood estimate. You just differentiate the log likelihood, okay? Now, it turns out that this has all kinds of properties. The maximum likelihood estimate is not in general unbiased, okay? But it turns out it's sort of asymptotically unbiased, which is that, the variance of the estimator, or the mean square error of the maximum likelihood estimator asymptotically achieves the Kramer-Real bound, okay, which is the lower bound on the variance of any unbiased estimator, okay? So it's so-called asymptotically efficient. So you need to take a course in statistics, and I very briefly summarize it here, and you can read it. Like, everything you need to know is here, except for you'd have to read every sentence 50 times, okay? But try to understand it as best you can, but you should probably take a course in statistics, and you might also want to go off and read some wiki pages, okay? But the bottom line is this: there's a thing called the Kramer-Real bound. The Kramer-Real bound is a lower bound on the variance of an unbiased estimator, okay? So you can't ever do any better than the Kramer-Real bound. And the maximum likelihood estimate gets asymptotically close to it as the number of observations goes to infinity. So you can basically make the argument that for large amounts of data, you can't do any better than the maximum likelihood estimate. You can do it like a little better, but for all intents and purposes, it's about as good as you're going to get, okay? Now, there's some notable exceptions to that. Like, sometimes you divide like n minus 1 when you're computing the variance. That's good. You can do a little better than the maximum likelihood estimator, we'll see. But mostly, it does about as good as you're ever going to do, okay? Now, let me do a simple example. Okay, so we're kind of running out of time, and I got a lot to cover. So there's example 2.3. Okay? You need to go through these examples very carefully, and they're homework problems. So, you know, the danger here is you look at this thing and you go, yeah, that's right, oh, that looks good, okay, let me go out and get a beer. Okay, well, maybe you don't drink beer, I don't want to offend you. Okay, but whatever, no. You gotta, like, hide it and do it yourself. Because it's easy to just read the thing and say, oh, yeah, it looked good, okay, yeah, right, okay? I've been there, too. I tried that one, too, when I was your age, okay? But the thing is this. You got to do it yourself because you can see where it goes wrong. Derive it. And you can show that if you have a series of random variables, so you have y1 through yn, okay? Now, a standard assumption here will be that these random variables all have the same distribution and are jointly independent, okay? So when that's the case, we write I, V. That means independent and identically distributed, okay? So that's a very important concept, and it's central to the whole Frequentist deal, okay? Because the central theorem of the Frequentist belief system, okay? The world in Frequentist estimation all revolves around the center of their universe is, guess what? Any guesses there? What do you think is the center of the Frequentist universe?
Independent.
Independent and identically distributed, but what's the core theorem of their belief system?
Is that the parameters are real numbers?
Yes, but the theorem, that assumption. Any guesses? It starts with the law of large numbers, okay? They love the law of large numbers because it's the central belief that it's the way that they prove all the results. And the law of large numbers, for the most part, is based upon the assumption that you have independent observations of the same thing. See, Frequentists would say, Well, you know, it's ridiculous to say that the mean is some random variable. All that it is it's some number. So I can't estimate the mean of a random variable from just one observation. I have to have multiple independent observations, and from that somehow I infer something about what's going on. I've seen the same thing more than once, okay, independently. And from that I actually figure out what's going on. So that's why the frequentist view, okay, so you see it frequently, okay? So then from that, okay, so then you make that assumption, and here we're going to assume that they're normal, which is Gaussian, with mean mu and variance sigma squared, right? Yes. And we can show then that the ML estimate, we can do the calculation, and the ML estimate, guess what the maximum likely estimate is? So, okay, if you have an observation, okay, the ML estimate of the mean. So here, theta is the vector mu and sigma squared. So the pair of parameters mean, mu and sigma squared form the vector parameter theta, okay? And now what's the maximum likely estimate of mu? Just guess. It's going to be a sample average, okay? So it's 1 over n, sum from I equals 1 to n of yi. Is that true because I told you it was true?
Well, now they're really conflicted because they're thinking, well, I really don't want to piss them off because I need a grade in class. But, do I really believe it just because you told me? Well,
what do you think? Is it true just because I told you it's true?
You can prove it, can't you?
You can prove it, okay? It's not true because I told you it's true, okay? I know you always kind of like to make me feel good, okay? And let's face it, most faculty respond positively to, you know, unjustified accolades. But it's not the way it's supposed to be. It's supposed to be true because you can prove it. You're not supposed to believe me, okay? You're supposed to prove it yourself, okay? So what is the sample, what do you think is the maximum likely estimate of the variance?
Standard deviation. No, sorry, it's the variance.
It's the sample, yes, it's a sample
variance.
Sample variance. So it's going to be 1 over n times the sum from I equals 1 to n of yi minus mu hat squared. Now, is this true because I told you it's true? Yes or no? Say it with passion. No! Has anybody ever seen the movie Network? Okay, I'm going to get myself into real trouble because I usually do this stuff, but now I'm on like trouble to TV. But I'm mad as hell, and I'm not going to take it anymore. No, it's a classic movie. Yeah, no, it's not true because I told you it's true. It's true because it's true. You can prove it. Okay, and you're going to do that. You have a question?
So if you wanted the standard deviation, you take the square root, but then you don't have the maximum likelihood estimated of the standard deviation.
It turns out you do, and it's a very simple proof, okay? And you prove it that any function of a parameter, so let's say you have a one-to-one function. So the standard deviation and the variance are related to a one-to-one function, right? A bijective function, the square root operator, the positive number, okay? So if you have a one-to-one mapping between two different variables, the maximum of two different parameterizations, the maximum likely estimate of one is the maximum likely estimate of the other, properly interpreted. Okay. Okay. So that's one of the desirable properties of the maximum likely estimate. If it didn't have that property, you'd be like, I'm a little suspicious because why should I get a different answer if I change my coordinate system? Okay. But prove it. Okay. So now, okay, fine. Okay, so this is the mean and the standard deviation. Now, some of you may have seen the formula divided by 1 over n minus 1, right? That's not the maximum likely estimate. But it turns out that actual estimate, you can actually show, has uniformly lower variance, but it's not, and it's actually unbiased. It's unbiased and has uniformly lower variance. So this is sort of a good counterexample. The maximum likely estimate is not necessarily unbiased. In this particular case, it is biased, okay? and its variance is not the minimum variance, because there's a uniformly lower variance unbiased estimator, okay? But it's still pretty good, and as n goes to infinity, it's just these are the same, okay? Now,
So when you say uniformly, you mean like for different values of parameter, or?
yes, so in other words, you can make the argument that if you divide by n minus 1, this is better in all cases.
Of parameter pay.
Yes, it's uniformly better for all values, independent, it's just better. Sometimes, usually it's not the case in statistics, you can say something is better, okay? All you can do is to say you like it better, okay? Because sometimes it's better, but sometimes it's worse, okay? So usually, and that's actually what this course is going to all be about. Because this course is going to be about when, in the nasty cases, when you can't say something's better always, okay? By the way, this concept of being uniformly better, okay, it's a simple abstract idea. Let's say you have two functions, okay? So you have one function that's like this, okay? And I wish I had a different color chalk. But you have another function which is like this, okay? Well, which function is larger?
Depends on your value of x.
Yeah, I mean, here it depends. Neither function's larger, okay? Most things in life are like that, okay? You say, well, which car is better, okay? A Ferrari or a Volkswagen? Beetle, okay? Which is better, a Ferrari or a Volkswagen Beetle? I want to be specific. So Ferrari, I don't know, what's the new hot Ferrari? I haven't even been following them, but what is it? 599. The 599.
I think that's uniformly better.
No, because it costs more money, okay? Okay? And it has higher maintenance or something, or it's not as good as for carting the kids to school, okay? So it's not uniformly better, okay? Okay, I'll give you, it'll be pretty hands-down solution, okay? Because I could sell one and buy the other, okay? Okay? So actually, this is one of the fundamental issues in engineering, trade-offs, okay? That things are, but if this functions like this, and that functions like that, this is uniformly larger than that, okay? By the way, you should take like some real analysis if you haven't seen this stuff before, because it's where they go through all this. Yeah.
So is it the mean square error that's uniformly better? Like it's uniformly,
the mean square error is uniformly better. So, right. So you're going to read this. Okay. Now, you can generalize this. So the beauty of this class, by the way, is that I can come up here and make sweeping generalizations that are mostly true and enjoy myself, and you have to go back and prove this and sweat bullets, okay? So I get all the fun and you get all the hard, painful work, okay? But you're going to, the next one we're going to do is very important. It's this problem 2.4, okay? And what's going to happen is that, let's say you have x1 through, I should get softer chalk, through x n, but each of these things is a member. So xi is a random vector, and it's a member of r to the p. Okay. So each xi is now multivariate Gaussian. Okay. With mean mu, where mu is a vector, and covariance R, where R is a positive base definite symmetric matrix. Okay? Now, what we can do then is grind through a lot of nasty mathematics, which I'll let you do. Okay? And Wikipedia is your friend on this. And you can write down, well, first of all, one thing, equation 2.10 here is very important, because it shows a simple, compact way of writing down the joint distribution. So you need to derive that equation from basic principles, okay? Because now what we're doing is we're observing a sequence of vectors, okay? This thing here is sort of a matrix because its height is t and its width is n. You're observing n independent vectors, each of dimension p. And from that, you can write down the joint density of those vectors in compact form in equation 2.10, which I'm not going to attempt to do right now, okay, because it just would waste time in writing it down, and you're going to look at it in the notes. This is why you have to read the notes, okay? What is really important to do before every class?
Read the notes.
Read the notes. Thank you. Now, so if you compute the maximum likely estimate, the maximum likely, what do you think the maximum likely estimate of the vector mean is going to be? It's going to be the sample average. So actually, the equation is formulated the same. It's the same equation, okay? So the average is the maximum likely estimate of the mean. The average and the mean are not the same thing. One's a number, the other one's a random vector, but one is an estimate of the other, okay? And what do you think the sample? What do you think the maximum likely estimate of the covariance is going to be? Or autocorrelation, or whatever I call this matrix R, I forget. In the notes I have a consistent way of naming it, but what do you think it's going to be? I'll put here R hat is going to be equal to, it's going to be the average of something, right? So it's 1 over n. It's going to be the sum from I equals 1 to n of what? I'll take xi minus mu hat, but now that's a vector. So I can't square it, right? If you guys square a vector, I'm going to be very unhappy, okay? So what am I going to do? I'm going to take it, that's a column vector, so I'll multiply it by its transpose, and that's the sample covariance. So the sample covariance is the maximum likely estimate of the covariance. Okay, so that's all very nice. Now, I can also see the case of the Bernoulli random variables, oh, this is a really important case. I'm kind of running out of time, actually. And, I think I went a little slow here, but it is important. If I have Bernoulli random variables, so the Bernoulli random variables are x like 1 through xn, and each one is equal to, say, 0 or 1. Okay, so the probability that xi equals 1 is equal to theta, and the probability that xi equals 0 is equal to 1 minus theta, right? So if I observe n of those things, so if you have a coin, right, and you're flipping it, heads or tails, right? So, and let's say I know it's an unfair coin, okay, but I want to estimate what the probability of it coming up heads is. Okay, now clear your mind of all the advanced mathematical thoughts you have, okay? If I just walk up to someone in McDonald's and I ask them, I did something, like asked if the person was happy or sad, okay? And I counted how many people were happy and I counted how many people were sad, okay? What would the estimate of the rate of happiness be?
Number of happy people divided by everybody.
Yes, okay? I mean, it's the only logical thing to do, okay? So the estimate of theta hat, what you do is you just take what I call n1 over n. What is n1? n1 is equal to the sum from I equals 1 to n of delta of xi minus 1, okay? It counts how many times x is 1, okay? It's simplicity itself. You just vote, okay? You count how many people are 1, and then you say, what percentage of them are 1? That's not the rate, it's an estimate of the rate, because it's noisy. I can estimate the variance of this thing too, okay? Now, I'm running out of time. Okay, so next time, what we're going to do, so this is all the Frequentist framework, okay? Next time, we're going to talk about the Bayesian framework. In the Bayesian framework, and you're going to read the notes on this, so we can really blaze through it. I'm going to pick up the pace on this stuff, okay? In the Bayesian framework, the idea is that the thing we're estimating, theta, is going to be a random variable. So now what we can do is we can do things like minimum mean square error estimate. Okay? So see you next time. Bye.
Yeah.
Green space number